This lesson is about logarithmic functions and graphs. We just recently finished our exponential functions, and really logarithmic functions are the inverses of exponential functions, and so it'll tie in 5.1 and 5.2. Because exponential functions are all one-to-one, then when we create their inverse, the inverse is also a function. The inverse of an exponential function is called a logarithm. And so we've got a new word to throw in there, and you just have to know that a logarithm is the inverse of an exponential function. There's different ways, people work about remembering that, but this is the definition of a logarithm. The logarithm, y equals log base a of x. This should say is that number, is the number y such that x would equal a to the y. So let's just pause for a moment and think about that. When you see a logarithm, here it says y equals a log. But y over here is an exponent. If y is an exponent and y is a logarithm, then a logarithm is an exponent. And so it's just going to work like exponents, and that's not going to happen so much in today's lesson, but in the future that's going to be an important point to get. Notice that when I read this, this is log base a, and over here, because the a is raised to a power, this is also base a. So they have the same base. X is greater than 0. Notice where the x is. X is what we're taking log of. Again, when I read this, it was log base a of x. That's actually called the argument of the logarithm. But that is kind of what we're putting into the logarithm, not the base of it. It is always positive. And that's because over here, when we were doing our exponentials, if we had a positive number and we raised it to a power, we kept getting a positive. And so the answer to that was a positive. And so this still tells us that a is positive and it's not 1. That is coming directly from that exponential function section. So if you look at this, the gray one shows you what an exponential growth looked like. If you reflect that over the line y equals x, which an inverse is always a reflection over that line, you'll get this red one. And this one is what the graph of the logarithm looks like. And again, over here, if we had an exponential decay where it was getting smaller, and you see that in gray, if you reflect that, this red line is the logarithm that will go with that. So if we have a base that is a positive fraction, less than 1, number between 0 and 1, this is what our logarithm looks like. If you have a logarithm with a base bigger than 1, this is what the logarithm looks like. However, the easiest way to graph logarithms is not to actually deal very directly with the logarithm. So I'll show you what I think is the easiest thing going, unless of course you're using your calculator. Whenever we find an inverse, we trade x and y, and then you solve for y. So if I were to take this equation here, y equals 2 to the x, it's very easy for me to trade the x and y. But notice, how do I solve for y? How is it that I can get that y down out of the sky over here? Well, I know that this is cheesy, but this is where you're going to have to say, oh, that's way up in the, like a tree. That one's so high up in the air. How do you get a tree down out of the air? You make it a log. Okay, that was really cheesy, I know. I'm almost ashamed. But what we will do to get this y by itself is use our definition. And the definition, I'm going to back up to it. Notice this says x equals 2 to the y. The definition said if x equals a to the y, then y will equal log base a of x. So if my a over here is a 2, then I'm going to put the a over here as a 2, and I'll say y equals log base 2 of x. And logarithms then are how we get exponents kind of on ground level up out of the sky. Okay, so they're no longer floating exponents, and we can deal with them a little bit differently. So y means the power that you need to raise 2 to get x. But saying the power that you need to raise the base to get the argument is going to get rather tiresome. So after a while, you will get used to it, and you would rather say logarithm or log. I know that when I very first learned this concept, I thought, great, not only do we have letters in here, but now they're throwing words in as well. But it just takes some practice. So here we're going to do this by rephrasing it. Technically, we shouldn't need a calculator for these. This means, what is the power? That's what a logarithm is. What is the power that you must raise 10 to? That's really what it's asking you to think of. What is the power that you need to raise 10 to get it to equal 10,000? All right, well, 10 to the first is 10. 10 squared is 100. To the third is 1,000. 10 to the fourth is 10,000. So that answers 4. And again, 10 to the what power is 10,000? 10 to the fourth. Now this one can throw some people off because it got smaller. You think 9 to the what is 3? Well, anytime, and we see this getting smaller here, anytime something's getting smaller, there's only 2 options. It's actually a root, or it's a negative exponent. 9 has a nice square root of 3. And so what you really have to know here is that the square root of 9 is 3. But that square root right there can be rewritten as 9 to the 1/2. The root that's in front can become the denominator in a fraction. So 9 raised to the 1/2 is 3. So 1/2 is the power that we need to raise 9 to get 3. If you've got a decimal, sometimes it's helpful to rewrite it like a fraction. So 0.01 is the same thing as 1/10th, 100th, okay? To move something to a denominator requires a negative exponent. So if I just put a negative out here to say I'm going to have to raise it to a negative power, that would move 10 to the denominator, and I'd have 1/10. But if I need it to become 100, then I also have to square it. So really, this one is equal to -2, which means that I had to move it down and square it. Now, another way people think about these powers of 10, which we have on both A and C, has to do with decimals. This one has 1, 2, 3, 4 numbers behind it, so that's a 10 to the 4th. On the other hand, this one moves 2 places to the left, so that's a -2. So that's another way to think about those and get the 4 and the -2. Now 5 raised to what power is 125? Well, 5 to the first is 5. 5 squared is 25. But 25 times 5, that's 125. So that's going to be 5 to the third. What power do we need to raise 6 to get 1? Well, 6 raised to what is 1? Anything raised to the 0 power is 1. Anytime you have a 1 right here, you're going to get a 0 over there. 5 raised to the what power is 5? Well, 5 raised to the first is itself. So you can see that we've just kind of really thought those out in terms of not just saying log base 5 of 5. We just had to rephrase it and think about what it means in terms of a power. However, sometimes we just need to rewrite these things from one form to another, and this may look a little bit blurry to you. It was a little bit too complicated for me to retype so that you could see it. But again, y is an exponent. It just doesn't look like it when it's in logarithmic form, but it does look like it over here in exponential form. The b right here is the base on both of these. A handy little tip is to start at the base. Just focus your eyes on where the base is, and then move to the other side of the equation and then back. So what is this example of that? Well, first of all, what is the base here? The base is 2. So if I start my eyes here, and then I move to the other side of the equation, and then back, what I'm saying is that to rewrite this, I could write 2 to the y equals x. Sometimes we just need to take a logarithmic form and write it in exponential form. Now, if it's in exponential form and you want to write it in logarithmic form, so let's do another example. What if it said 3 to the y equals 9? Now, it's not asking me to solve it, just rewrite it. Well, this is the base, and there's the other side. So that translates to log base 3 of 9. Now, where did the log come from? Well, I do have to keep in mind, since this one is in exponential form, when I rewrite it, it'll need to be in a log form. And then go back to the other side, equals y, or y equals log base 3 of 9. So those are just rewrites. And sometimes you simply just have to do that, and you will have to do that in the homework. So here's some practice with rewrite. Again, you look at, first of all, at the base, then go to the other side and back. So it's kind of like a loop. So I'm going to say 2 to the 5th is 32. And that's true. A to the 8th is Q. This one's written the other direction, but I'm still going to use the same idea. Across the equals and then back. So T to the X equals M. Now these are not in logarithmic form, so I will use a log every time I write one of these. But I have to identify the base. I'm going to have a base 2, so it'll be log base 2 of 16 equals x. Find the base. Log base 10 of 0.001 equals -3. Log base E of 70 is T. These two are special. And that's what's going to come up on the next slide, I believe. But no, really, even though I wrote log base E and log base 10, nobody ever really writes those. 10 is like our understood number. If you don't see a number there, it's going to be 10. And E, actually, log base E gets called something else. So let's look at our next slide, because those two are special. Logarithms that are base 10 are called common logs. The base 10 is understood, and it's generally not written. So they're just going to write a log. So let me go back on that one for just a moment and say on this one, instead of writing log base 10, they would really just write log of 0.001 is -3. And if you don't see a number right here, it is understood to be 10. Now that's handy because that is actually what this key is on your calculator. This is log base 10, and notice the second function of it right here. The second function right here is 10 to the x. So the 10 is the base, and it's the base on the log. Now we pressed this key earlier when we used E in our last lesson, but we did second ln. E to the x, well, the base is E. ln is log base E. Logarithms with base E are called natural logarithms. Now, in other languages besides English, you know, the adjective often comes after the noun. So if we put the natural behind it, that would make sense why it's ln. And your calculator has an ln key. Be careful. Notice that this ln key is in all capitals, and so there's no doubt there's an L. But when I type this over here, it's in lowercase, And that L could look like an I, but it's not. It's an L. It's ln. Why am I stressing that? When you need to do ln on your homework, you're going to have to type in ln. And I had a student in the past who kept missing it and didn't understand why. And it really was hard to see, but they were typing a capital I. So that's not a capital I, that's a lowercase l, ln. So we have ln for base e. So once again, back on this page, they never really write log base e. They would just write ln, and I'm doing it in cursive there so you can see that loop on my L, ln of 70 equals t. So two special bases. These problems are calculator problems. Generally on logarithms, the rule is to round to 4 decimal places. That's kind of actually a leftover. There's no real reason we have to have it to 4 decimal places. But years and years ago, when they didn't have calculators that did all this easily, people had made charts, and the charts went to 4 decimal places. So here to do these, it's just log 0.57. Now, if you only enter one log, it's not important that you close parentheses. But if you have something else that you're doing math-wise, like if you were doing a log plus something or anything, you don't want to close parentheses. So it's kind of a good habit to get into. So that's our first answer. And then I have log of -2. Oh, do you see this I? That's because my calculator is set in imaginary. So if I go back and I just set this in real numbers, and I redo that problem, notice it tells me an error. That's because it's not real. Whenever you are taking the logarithm, you might not remember this, but up here, this x had to be a positive number, and it's also a real number. So it has to be positive and real. And now -2, when we look at that, -2 certainly is real, but it's not positive. So really this one, as well as this one, are going to be not real. It's undefined. Probably on your homework it would say D and E. You would get an error message on both of those. Now I can click go to, and it will tell you, yeah, as soon as you told me to take a log of that, I had a problem. But let's just clear that. So since I know that one's not real, I'm going to go back and type this one so I'll get my answers all on the screen. Log of 0.57. I'm going to skip the one that's not real, and now I'm going to do ln of 2. And ln of 809.3. So I have those answers. And then our last one, again, was not real, so does not exist. You can actually use your calculator on other bases too. There is a change of base formula, but you're not likely to have to actually use it because our newest calculators have that formula programmed. So you can find it underneath the Math menu. And so I'll show you that in just a minute, but if you go to Math and then you scroll down to A, or you could scroll up to A, you're looking for the one that says log base. So we're going to show you how both of these work. What this says is if you have a base that you don't know what to do with, you could just change that into a division problem as long as you have the bases the same. So you could use any base you want to, but the ones you would want to use are the ones on your calculator. You would either want to use base 10, which is your log key, or ln, which is the base e. So if I want to do this one, and it says use the change of base formula, well, again, when your homework tells you to use that formula, you might actually be able to do it without the formula. I'm going to start right here with this one. I could, on my calculator, type in log of 25 divided by log of 4. Now, when I type that on my calculator, it automatically opens it. So since there's more math to do here, you would definitely need to close it. and that's what I was mentioning earlier. I could also just use my ln key and do ln of 25 divided by ln of 4. But what I really probably want to do is use my calculator program. So I'm going to bring the calculator back over, and we're going to do that one all 3 ways. So I can enter, and I can use the fraction key stuff if I want to. Alpha y equals enter, and then I can have log of 25 over log of 4. Or I could do ln of 25 divided by ln of 4. Or the change of base program that's built in is underneath math. So I'm going to hit math. And then you can't see it on your very first screen, so you can either scroll up or scroll down. It's just a little ways to get there. And you'll find it by A, and it says log base. Now, if your calculator happens to not have this, you're just going to need to do it this other way, which isn't too difficult at all. But if you have this log base, then you can see when I press that, it is ready for me to enter the base. And so I can say log base 4 of 25. Exact same answer. So here is the calculator program, but this is actually the way that it's calculating it with the change of base formula. So that one ends up being approximately 2.3219. Why would I do this a hard way when you can do it the easy way? I'm not about making things harder for you. Math. Now, instead of scrolling all the time, if you want to, you can just get there by hitting alpha math, because alpha is going to be an alphabetical choice. And then math has the A on it. And that's actually a nice shortcut, since I know it's option A. So negative 0.2614 math, and then alpha math. Put in my 200, log base 200 of 50, 0.7384. Math, alpha math, and that was base 9 of 100, log base 9 of 100, and so we just couldn't possibly do this in your head. 9 to the what equals 100? I have no idea. 2.0959. 0959. Now this does make sense to me, because 9 squared is 81. So it had to be bigger than 9 squared. But 9 cubed is 273, so it's not nearly a 3. It's just barely over the 2. So we've used our calculator and change of base formula or the change of base program to do other problems that we can't do without it. So now we're going to look at the graphing. How do we graph these? Well, generally speaking, I know you could use your calculator and you can get some things, but if you're going to learn to understand the math, what we want to do is think of the related exponential function. So the function that would have the same base. First of all, think of y equals, now this is base 3, so think about y equals 3 to the x. If I were going to graph y equals 3 to the x, I would plug in -1, 0, and 1. Then I would have the -1 would do a reciprocal 1/3. Anything to the 0 is 1, and anything to the 1 is itself. So I would have those points. Then, if I want to do log base 3 of x, what I know is that these are inverses, and inverses trade the xy values. So I would have 1/3 -1, 1, 0, and 3, 1. And then I can graph these. So 1/3 is barely over, and then 1 down. and then I would have 1, 0, and then 3, 1. What happens is that instead of having that horizontal asymptote, what we now have is a vertical asymptote. And it should reflect over that line y equals x. Now sometimes you'll be asked to graph them on the same coordinate plane. I think I have one of those. But this is the process. And then if we have to shift it, we can shift it from these points. This one has multiple shifts, or stretches, compressions. But what I want to very first do is think about the related exponential function. So the base here, it's that understood base. The base here is 10. If I were going to say, all right, let me think about y equals 10 to the x. So the related equation, -1, or related exponential equation. If I plug in a -1, I get 1/10. With 0, I get 1, and with 1, I get 10. Then for just the log base 10, which you don't need to write down, of x, I just need to reverse those. So I've got x and y. And I am kind of writing this bigger and leaving myself some space because I know of something yet to come. So, and that's going to be with me doing some stuff here to get all of the rest of it taken care of. So first of all, just the reverse, I can have 1/10 and then -1. 1, 0, and 10, 1. So now let's look at what we can do for some of the other things going on. What this does right in here is this is a shift that actually goes to the right 1 unit. So if I want to go to the right 1 unit from my x's, I can add 1. And what that does is that shift to the right 1 unit. Then the next thing we would look at is this 1/2. But this 1/2 is not in there with the x's. It's half of that result. So I need to take half of this and subtract 2. See, that's happening to my y values out here. The half, and then subtract 2. Shifts that happened with the x, I adjusted my x. Shifts or compression stretches that happen with y make me adjust the y values. And so the result, this will be 1 and 1/10, which is really 1.1, 2, and 11. Again, I just added those. Then over here, I have -1/2 minus 2, which is -2.5. I have 0 minus 2, which is -2. And I have 1/2 minus 2, which is -1.5. So if I graph those, I know that I am just past 1. This is marked off at 2, so really just past 1 and down 2.5. I go over to 2 and I am down 2. And I go over 11 and I am down 1.5. I wish I was going to be able to connect those beautifully, but what's happening is a curve that should connect those, and mine will miss them, no doubt. So I usually can go this direction better. Yeah, it was way too low there, but. So anyway, I did some manipulation of the points. Hopefully you understand what I did, but I am not saying you can't use a calculator to help you do some of your graphing. I get that. But you should be able to identify what is happening with our shifts because we've had that in a previous lesson. Graph both functions on the same coordinate plane. Let's do this one in green. And if I'm going to graph that on the same coordinate plane at -1, I will be up at 1/3. At 0, I would be at 1. And then at 1, I would be at 3. Now you can plug in more numbers if you want to. So like at 2, I would be at 9. So you can see that that's getting really steep. And I know it should level off there. I do know that the other one is a reflection of it. So I can take those points and reverse them. So instead of -1 1/3, I'm going to go 1/3 -1. Instead of 0 1, I go 1 0. This point right here was 1 3, so I need to go out 3 1. And if you wanted to reflect this one, this point here was 2 9, which means I can go 9 . Don't know why. Never know about the internet, do you? They're the reflection over this line y equals x. It's going to be very important that you can identify those points, not because you're graphing by hand, but because when you take your shape and put it on your graph, then you have to move some points to the specific right place. And so that 3 points will help you get that curve in the right place. That really finishes the concepts, but I've had some homework questions on this specific problem, and I think it's just too many words because it's not really that hard of a problem. This formula right here is given, and it's how they determine what the Richter scale is for an earthquake. Now you could look up what this is, but this I sub O is like the smallest intensity possible. This, it was 10 to the 7.8 times that smallest possible intensity. And then it asked us, what's the magnitude on the Richter scale, which really means us that we need to find R. Well, R is equal log of the intensity over I sub O. So this intensity, I need to substitute right here and say it is 7.8 times I sub O. But then the I sub O's divide out. So I have log of 10 to the 7.8. If you just think about logarithms, we could work this one out. You could pull up a calculator, but I know that this has an understood. So that is 7.8 on the Richter scale. But if you didn't think of that, you could put that into your calculator. So this problem's not nearly so hard as it looks like, but it was confusing to some people. So I hope that helps you out. Sorry about the connection issues we had. Please get in touch if you got some questions, and hang in there. You're almost done. There's just a few sections left in this course.